Hi, I'm John from VistaSend Solutions, here today to talk to you a little bit about advanced policy logic. In a previous video, we talked about the introduction for policy logic, which is something we call thinking in policy. It went through various structures and formats in order to create commonly used terms in computer science, ands, ors, some of the more basic logical operators. Taking it a step further, we are going to go into more advanced routing. We are going to look at the concept of or and then take that to a much more advanced level. So from our previous version, you saw that we had these two images out. It was a graphical representation of an or statement and an and statement. Now in this case, Layer 7 chooses to use ors as at least one assertion must evaluate to true folder. And we can see that up in the policy manager here now. We also have the concept of and, which Layer 7 calls all assertions must evaluate to true. Remember, an assertion at its basic foundation is either a true or a false. Some assertions will automatically evaluate to true, and some may evaluate to true. So looking through here, we can see that in the concept of or an at least one assertion must evaluate to true, that ors will always evaluate true, except for when both sides of the equation are false. So if you think about it in non-computer science terms, if an apple is a fruit or an orange is a fruit, those are both true. If you say, if an apple is a fruit or a hammer is a fruit, that is a case where one of these will be false. If you say, if a hammer is a fruit or a chainsaw is a fruit, obviously both false. And similar with and, except for both sides of the comparison have to be equal to true. And so we can see that, and we saw that in a previous video on how these basic logic flows work together. Now, like I said, taking a step further, we want to introduce a couple new terms. So new terms here require a little bit more advanced display. So I want to thank my discrete mathematics professor for going through truth tables because this ended up being a nice little blast from the past. So we have the concept of A or B, and we outlined all the possible combinations. Either both A and B are true, either one of A and B are false, or A and B are both false. And that gets us the evaluation where we can look at A and B, which only evaluates true if both A and B are true, false otherwise. A or B, which always evaluates true unless both A and B are false. And then a new concept. So this is an exclusive or an XOR, which is much more prominent in computer science. So any programming languages will probably have a concept of XOR. I have put the relevant Java notations down below. And what an XOR does, or an exclusive OR, will evaluate true only if one or the other are true, not both. And that differs a little bit from the OR, which we've kind of put them right next to each other for a reason, in the concept where ORs are short-circuiting operations. So when we have a short-circuiting operation, like we mentioned before, Layer 7, in this case, will short-circuit at least one assertions, or ORs. If A evaluates to true, or the first comparison in the expression evaluates to true, then it will not evaluate B or C or D or however many logical operators you have in place. This is not the case with exclusive OR because it needs to make sure that only one of these statements are equal to true, and not both. And so what we've done is we've set up a little bit of a comparison here. Now the one thing that we didn't talk about is the not operator. In Java, you would use a bang or an exclamation point to negate any value. So if you had a Boolean variable that was equal to true, you could negate that and it would be equal to false. So it's going to take the opposite of whatever value that expression is. In layer 7, this is much easier. We have the ability to compare variables to each other. So instead of a comparison, we would have a does not equal or a not comparison. And we'll show what that looks like in a second here. So either way, we are going to go through all of these today, and then we're going to show you some of the more useful patterns that go within the Layer 7 gateway when it comes to logic flows. So first thing, we will cut over to this first test, and I created a policy just called Advanced Policy Logic, ADVPL. We are going to have 3 variables here. I'm setting them as strings just to make this very apparent what is going on. You can do this with numbers. You can do this with sometimes messages. You just have to make sure that you are setting out the right variables. You can do this with integers, pretty much any variable that the Layer 7 gateway will handle. So looking at our first test, the comment here says A and B or C. So we're going to talk about how to do this 2 different ways, mostly because the expression A and B or C is a little bit ambiguous. So we'll go through that. We are going to look at A and B or C. So when we look at more advanced logic, it helps to have more variables in play. So we can use some of these methods together, some of these logic operators together. And so we come through, we say in this case, we are going to do an all assertions must evaluate to true. So we are going to do the and up front, but we are going to put that within an at least one assertion must evaluate to true. So that's going to be our or operator. So if we take this as a and B, we'll minimize that out. We'll see we really have an A and B or C. And so when we were talking about short circuiting before, this is where performance comes in handy. So we have the capability here to potentially allow C to be the first variable compared. And if C evaluates to true, then we're not even going to look at what A and B can equal. So when you're creating your logic, when you're creating your policy, there is a performance aspect here. There's also a logic aspect here. So if you want this to be essentially a short-circuited value, where if C for whatever it's supposed to be is equal to true, we don't even worry about this. And this could be other operations down here. You want to make sure that you have C first, since this will always evaluate in top-down order. So let's move this back. And we are going to run this test right here. So I have everything else commented out. So we'll come in here. We can see that A is true, B is true, C is true, A and B or C equals true. So if we start playing with variables and change this to false, we will see that this is changed to false now, but this message A and B, which does evaluate to true, or C equals true. So this is an example of short-circuiting that statement. We're not checking C at all. Now if we change this to, if we change variable A to false, and save and activate, we can see that this statement did not evaluate to true because the A and B was false and the C was false. Now if we come back here, move C back to true, and then change this in the logical flow to be above, you'll see a short-circuiting that and now. So A and B or C evaluated to true because this really turned into C or A and B. So the order is very important when you're dealing with at least one assertion must evaluate to true, or statements. We are going to disable this and re-enable the second test here. Second test, very similar to the first test, except for we have differences in operators. So instead of having that A and B or C, we're going to have A and B or C. So it's very similar to the modification that we used in this last step. However, I want to show that you can, how you place these parentheses, or the logical parentheses that we're inserting here, can absolutely make the difference in how your policy works. So the logic becomes very important here. So similar to when we had C up above and then the all assertions, the and comes down here, we're going to have something very similar. So in this case, we are going to have A and B or C. So in this case, everything has to, or either A, which is going to be equal to false right now, has to evaluate to true, and B or C. So essentially A has always got to be true. So let's set that to true. And then we will move, C to false to show that we're still short-circuiting even within that first statement. So everything's saved up, and now we can see that this is evaluating to true. So really what ends up happening here is, because A is true, B is true, we don't even look at C, because it's part of that, the second part of that or, once we've already evaluated this to true. So hopefully you can see a little bit how the order matters. All right, let's move this to true. We'll start out with a good full true statement. Now we are going to look at XOR here, which I have not written the test out for yet. And I did that for a very specific reason. There are ways in computer science to evaluate XOR without using the notation that we showed down below. So normally this would be a caret. Obviously we don't have anything like that in layer 7. When we start talking about different types, and especially in strongly typed languages, we want to make sure that we're talking about not just bitwise, but logical operators. So in this case, we have double ampersand for and, double pipe for or, a caret for XOR, and a bang or exclamation point for not. Now we don't have any of that here. Now we're going to show it to you in layer 7, where this is a little bit different. So in here, if we look back at the truth table, A XOR B is only false when A and B are true, or A and B are false. And similarly, A XOR B is only true when A and B are true and false, or false and true. We can take this down to a slightly lower level by saying if A and B are the same, then A XOR B is false. And so let's look at that comparison. And so we are going to create an A, and we're going to make a simple comparison. And we're going to say if A is not equal to B. Now for interests of this, we're not going to make this case sensitive. You can do that if you're looking at string comparisons. Again, this is something where you would not typically do XOR comparisons on strings, but you can certainly do them on integers, and we will show you you can do them on strings in layer 7, which is a little bit more of a flexible option. So let's move that up here. So now we have a true XOR. If A is not equal to B, we will return true. Otherwise, we will return false. And so we'll come in here. You can see that A XOR B is true. Now if we change this statement up, essentially negate the is not equal to, make it equal to, you have the ability here to also show false. So let's bring this back into a good state. All right. And so the last capability that I wanted to show you was less of a capability and more of a pattern. So if you're looking through this policy that we've generated, you'll start to see some commonalities through this. We'll start with an at least one, we'll go into an all, we'll have an at least one, go into an all. Hopefully you start seeing the pattern now here. So when we look at policy, and especially advanced policy, one of the main patterns you will find is a lot of logic flows will take this approach. We'll start with something, at least one assertion must evaluate to true, and then you'll go into all assertions, and then at least one. You'll kind of go every other through these. So I set up these just to show that there are possibilities to put in more data in here. Now finally, if any of you have questions about the return string that I'm using, all this outputs is just the form that we were seeing in previous tests with the nothing evaluated to true. Because if we start minimizing all of these tests, you'll see that they're all in this at least one assertion must evaluate to true, or an or statement. And so if nothing else passes, we'll just return a string that says nothing else evaluated to true, which means something evaluated to false. So again, my name is John from VistaSense Solutions. Hope you learned a little bit more today about advanced policy logic. Feel free to give us a like, subscribe, and comment if you have any questions. Thanks a lot. Bye.